All right, thank you for the opportunity and thanks everyone. So I'm Jagadish. I'm with Calico Life Sciences, part of the Alphabet family. So the title of my talk, From Endoscopy to Microscopy, Role of Machine Vision. I'm really thankful to Max to have set up the stage for me. I think that was, so I can sort of hammer in some of the same points that he wanted from a slightly different perspective. Because something I heard at this MICAI conference, which is like a medical imaging conference a couple of years ago, where the conference chair was essentially saying that, like over the last 20 plus years, you have had over 2,000 papers published talking about machine learning and deep learning, how it's going to affect surgery and clinical diagnosis and change patients' lives. And he could literally count on his fingers the number of those papers that actually got deployed in the OR and are actually making a change in patients' lives, right? So what exactly is the bottleneck? So I'm going to approach it more from a data and modeling perspective, and we're going to sort of dig through some of that. So I'm going to first talk through there's going to be some repetition with respect to what Max said, like how vision started to play a role in surgery itself, and then we'll go from there. So this is how surgery was. It's an iconic photo from the 19th century. So it really was a theater, a surgical theater. So I've seen some versions where somebody up here was smoking. I really hope it was Photoshop and it wasn't that way. But this is how it used to be done, right? And this is open surgery. And then laparoscopy in the late 1970s and 80s, with advances in like camera technology and video technology, really changed how surgery was performed. Like then instead of opening up the patient, you just had like 2 or 3 holes or incisions in the patient. One of them was for the camera, and the feed from that camera was essentially here. And then the others were for the tools. And the surgeon was literally looking inside the patient through a laser light source that was projecting onto the monitor. And they were moving the tools and literally seeing what effect it was having on the anatomy as they were doing the procedure, right? And then you had robotic surgery, which we saw extensively in the previous talk. So the difference here is that the surgeon is no longer in the sterile space. He's sort of not scrubbed in. He's sitting at this console, almost like playing a video game. The video feed is sort of coming up to him or her, and they are sort of wearing these sensors in their arms and literally sort of moving their wrists and fingers in the air. And when they're doing that, the robot that is actually positioned over the patient here is mimicking their arm and wrist motions inside the patient and essentially manipulating the anatomy. So they don't get haptic feedback. They don't actually feel the movement inside the patient, but what they're actually getting is the visual feedback, and as they're doing it, the robot is mimicking their gestures, right? So the big advantage of this is that now the surgeon is sort of free to move their arms and do as many gestures as they want, as opposed to laparoscopic, where the number of dimensions or degrees of freedom is really limited. And so the surgeons have to do a lot of things to sort of do the suturing and things like that, right? But there was also a downside that when we went from open to laparoscopic, it was a very clear win. There was much lesser bleeding. Patients went home quicker and surgeries were faster, and it was a win-win for everyone. But with robotic, the win is not yet as clear. Financially, robots cost more. The hospitals are still trying to make money out of robotic surgery. And outcomes-wise, it hasn't really pushed the needle as much as people thought it would, going from laparoscopic to robotic. So people are still trying to figure out how to make money off of robotics. But the thing is, it has taken off in some procedures like prostatectomy and colorectal procedures, and I really feel like it has sort of set the stage for democratizing surgery, if you will. So, but then, what is next, right? So then you want to talk about intelligent robots. So the robot we saw earlier is just a dumb extension of the surgeon's arm. Literally, it's just doing what the surgeon is doing. Surgeon stops moving, the robot stops moving, and it's not informing the surgeon of anything that is happening in the procedure. But then you want to sort of incorporate perception into the robot, and you want to be able to, with augmented reality and so on, be able to see and the robot to actually judge what is happening in the procedure. But a lot of this is hampered by sort of media hype, unrealistic expectations. Like when the surgeons come in, there's this whole spectrum of some surgeons actually being skeptical that the robot can do anything in terms of perception to others who are actually scared that the robot is going to replace them, right? And there is no, and we are somewhere in the middle, and the robot cannot even tell the liver from the kidney today. So it's really, like trying to start small and sort of build up from there. So there is really a gap between the need statement and what is actually available in terms of data and diversity. So I want to talk about something called sort of collective surgical consciousness, like starting all the way from pre-op to post-op. So I really feel like imaging data especially is under-integrated and sort of underutilized in most of the surgical steps. And if you look right from diagnosis, when the patient walks in, you have all these unstructured text in the EMR notes, the nurse taking down notes, and then you can use data mining techniques, but very rarely so it is combined or fused with the imaging data by a machine to sort of come up with what is the next step. So there are so many things that can go on here. So the patient has a CT or an X-ray, and then you have the notes, and if you can effectively combine that and add in that extra element where you are aware of the patient's specific need, like has the patient had some previous surgery, have they had an implant, are they an athlete? So all of these sort of determines what kind of procedure or what kind of recovery the patient is going to have, right? So that is the first step in terms of pre-op, where the vision can help in integrating some of the diagnostic data. And then you have intra-op, like as we already saw, we have the video feed sort of coming from inside of the patient. And if you can combine it with all of the other sensors that are there in the operating room, the vitals, like the blood pressure monitor, what have you, like all of those sensors together with cameras, anesthesia, dosage, it does not happen today. It's very siloed. Most instruments don't talk to each other. They have their own APIs. It's all proprietary. And there is really no one integrated way of combining all of this data and making a collective decision, right? And lastly, you have the post-op, where if you are aware of some complications that happened during the intra-op, you can sort of get that from the video, have that archived, and then combine with some of the post-op visits as the patient comes in for monitoring. You can sort of combine that with the aftercare analytics and eventually come up with a solution where the patient completely recovers and walks away home. So that, again, what we call like collective surgical consciousness, and in my opinion, vision can play a huge role in each of these steps, literally. And that's what I'm going to do in the next few slides. I'm going to take like one example of a disease and just go through how vision plays a role in each of those steps and how the stakeholders that the vision model can help also changes. So I'm going to take for pre-op how it can help the patient, for the intra-op how it can help the hospital, and for post-op how it can help the surgeon. Okay, so that's what we're going to look at. So the example is that of gallstones. And some of you may already know, but for those who don't, so gallstones are cholesterol or sometimes like pigment stones that develop in the gallbladder. They can range in size anywhere from a grain of sand all the way to a golf ball. And the first line of diagnosis for that is to get an ultrasound. And if the stone is large enough, the ultrasound is pretty conclusive, and a surgery is the immediate next step. But there are often times when depending on the size of the patient and the size of the stones themselves, it's kind of hard to distinguish from background tissue. And even between subject matter experts, there is sort of disagreements as to like, is there a stone or not? And here I'm just going to show a model that was recently put out, which is sort of like a next generation UNet. So it's a fully convolutional network where it's sort of going from this raw image to this semantic map where it's actually trying to identify where exactly is the stone. And they actually compared multiple models. Here they went from the image. So this was the ground truth that was annotated by the surgeons. And this was a traditional UNet. This was a ResNet backbone fully convolutional network. And this is the UNext. So I guess the UNext sort of differs in that it has these spatial pyramid pooling of skip connections, similar to something that Mascar CNN has. And then you can also see all these dense connections. And then there's also an attention layer that is sort of feeding back information from the lower layers to the upper layer. So essentially they tried to sort of calibrate this network to be able to come up with a semantic segmentation of where the stones were. But even here, if you look, the size of the data set that they're looking at is 5,000 images, all from a same equipment and annotated by 3 radiologists. And again, no mention of what is the inter-annotator disagreement even within the images, right? So those are the real key criteria that sort of stop this from going from just being a paper to something that the radiologist can actually use. So how do you get FDA approval on something like this with a wide diversity of equipment out there, with how the patient is positioned, with the different lighting conditions? So I think that kind of diversity and open sourcing of the data is not yet there, and that's what is kind of stopping us from taking that next step in some sense. Okay, now that we have diagnosed gallstones, let's say the next step is to remove the gallbladder. So the procedure to do that is called cholecystectomy. And similar to what Max was showing, there are 7 steps really in going from preparing the patient to clipping and cutting the gallbladder, taking it out, and then packaging it, and then eventually closing up the patient, right? So this is a very well-studied procedure. It's a very standardized procedure. Most likely, most times it takes only like 45 minutes from open to close. And there is one data set that has been put out that contains 80 such videos, and all of them annotated by one surgeon. So the annotations are extremely consistent. So I have watched a lot of those 80 videos, and after watching 5 videos, I could tell like which step was. So that basically means that the surgery is so consistent that I'm literally teaching the machine how that surgeon is performing surgery. And unfortunately with surgery, just like with Google Maps, there is no one way to go home, right? I mean, there is no one right way to do the procedure. And some surgeons may be right-handed, some may be left-handed, some patients may be bigger than others. So there is really no one way to actually do this right. And if I end up teaching the machine what one surgeon is doing, I'm teaching the machine that surgeon. I am not teaching the machine the whole workflow. And again, so this is a classic example of so many papers published on this. Everybody claimed, oh, with 80% accuracy, we can determine what step of the procedure is being performed. But why is it not out there? It's not out there because it does not generalize, right? And it's not going to do that unless we have the scale and the diversity in data. But just for completeness, how you go about doing this kind of workflow detection is essentially combining the different. So if you look at the intuitive robot, for example, they don't just have the video data available. They also have like what tool is being deployed, how is the tool being moved, and all of the sensor information. All of that can essentially be fused, and you can imagine a sort of like a Markov state machine here, which sort of combines the states of all of these different pieces of information to eventually tell you what is actually happening in the procedure, right? And the paper that sort of came out on top in this particular challenge used something called an EndoNet, which was actually, I believe, like a VGG backbone. So they did it in a 2-step process. They used the CNN to sort of break down the video into single frame, and every frame they sort of featureized it. So the EndoNet was essentially outputting a feature vector here, and that was put out to an LSTM, which was looking as far back as 30 seconds. So they were essentially looking at 30 seconds worth of video, and then using like a sliding window to determine what exactly was the step in the procedure that was happening. And this here is the confusion matrix that sort of tells you, given the ground truth, the 7 steps, and given the prediction, how's the model doing. And you can see that more often than not, the machine is only confused by the step preceding it or after. So there's not too much deviation, and it does pretty well, at least on this particular data set. So continuing on in the same vein, I want to talk about like what happens post-op, right? So now post-op, I want to talk about how this is going to help the surgeon. So really, when you if you look at the previous step here. Oops. So one of the key steps here is the clipping and cutting, okay? And when you want to do that, you want to be able to tell where exactly. So there is this common bile duct that's going from the stomach to the gallbladder, and then it's forking to the liver. If the surgeon clips the duct before the fork happens, the supply to the liver is cut off, and it could be fatal to the patient. And they really need to see very clearly where the fork is happening, and they need to be able to clip the side of the fork that is going to the gallbladder, and then they can extract the gallbladder out, right? Bright light images don't contain this kind of information. The green sort of highlighted duct that you see is not very visible in bright light images. So most likely what they do is they administer a dye to the patient called an ICG, which if you shine a different laser light of different wavelength will glow in a particular color, and then the surgeon can switch between the bright light and the other image and essentially say whether the clipping is being done at the right point or not. Now, ideally, this should be done intra-op, right? So they should be doing this before they are clipping it. But even if they don't, in a lot of teaching hospitals, you will see that the main surgeon is often not the one that is actually doing the procedure. A lot of residents come in, that's how they learn, essentially. The residents are doing it. And the surgeons are literally evaluating how the residents did by watching these videos, and they're evaluating them on these critical tasks. So they're looking at the task and saying, okay, how did this guy do in this clipping task? And that is how they take that next step, right? And they actually have, I'm jumping ahead a slide here, they actually have a scoring scheme of how do you, so ideally, you can get up to 6 points if you did the surgery right. So if you are able to see the two structures connected to the gallbladder, and the two structures are clearly seen, you get 2 points. If you get some cystic, I won't go to the medical jargon, but if you get like a clearance, you get like bottom 1/3 of the gallbladder is clearly seen, you get 2 points. So you can go anywhere from 0 to 6 points, and based on what the machine is actually looking at, or rather what the video is actually showing, the surgeon can actually score this resident's performance and actually help them take the next step. So this is post-op analysis where the surgeon is actually watching the video and evaluating the resident, right? Now, you can easily imagine a network which is looking at multiple streams, in this case, the bright light and the fluorescent. And once again, you can imagine a CNN for each of them, and then you fuse the feature vectors and eventually do a softmax output, or it could be a regression that's actually putting out a score. And so instead of the surgeon having to sort of watch through this, if you are able to segment the video, identify the step where the clipping is happening, translate it to a score, that greatly helps the surgeon in sort of evaluating this and taking the next step. So really, I think what we have tried to sort of do in this example is to see how the gallstones can be diagnosed with vision. It can help segment the workflow of the procedure during the intra-op, and how it can actually help in post-op analysis and in evaluating how the procedure actually was done. So I'm going to use this as a segue to sort of jump into microscopy a little bit, something that I do quite a bit at Calico. So what we saw here is an example of fluorescence. So you actually see a dye that is actually fluorescing at a particular color when a light of a certain wavelength is shown on it, right? So this has been used in microscopy for decades. That's primarily because when you shine just incandescent light on a cell that you're studying, like a yeast cell or a worm or whatever it is, you primarily just see just the outline of the cell, and it doesn't inform you much about the internal structural components of the cell itself, like what does the mitochondria look like, what does the nucleus look like. And so that is important, because when you're trying to do drug development and you want to see how a cancer cell is going to react to a particular drug, you want to give it a particular dose of a drug and see what happens to the nucleus, what happens to mitochondria. Is it dying? Is it looking healthy? And you want to come up with a way of identifying what is healthy, what is sick, what is not so sick, and so on. And that is how you screen compounds. So you screen compounds, and eventually you sort of shortlist them and say, okay, this is a set of compounds that is really going to work. And that's how the drug development pipeline really works, right? So fluorescent microscopy essentially is, I would say, a bit falls under the category of optical phenotyping. So phenotype is sort of a term that is used to see, to sort of represent how a particular structure is changing with perturbations. Like if you're giving it like if you're changing the media, for example, or if you're giving it a dose, or if you're doing a genetic perturbation, if you're creating a mutant, like what happens. So that's what people refer to as phenotypes. So in this pipeline of how you're doing drug development, where you're doing like perturbations and so on, the way optical phenotyping helps is saying that, okay, here I'm actually showing you 4 different fluorescent channels that is actually visualizing or rather 5 different fluorescent channels. That's actually visualizing 5 different organelles, or rather substructures inside the cell. So you can see the nucleus, the endoplasmic reticulum, the nucleoli, and so on. So what the scientists really care about, the biologists really care about, is under certain drug conditions or under certain genetic perturbations, how does the nucleus shrink in size, or does it grow in size? Does it sort of get fragmented? So that is what we really want to study, right? But then I'm going to sort of go to a slightly different kind of model here. So just like we don't like laser light being shined on us, cells don't either. So you can literally cook the cells by if you shine like intense laser light on it. So as much as we really want to study the internal structures of these cells with laser light, the more light you shine on the cells, the more you're actually changing the morphology by yourself rather than the drug actually doing something. So there was this model that was put out by the Allen Institute from MIT, where they actually Google has an equivalent model in 2D, where essentially they are saying that if you just give a stack of bright field images where the cells are just imaged using incandescent light, so that doesn't kill the cells are happy. And if you train it on a pair, let's say you shine laser light on these cells and you create a fluorescent change. So now you know what the bright field image looks like, and you know what the registered fluorescent image looks like. So you can train a 3D unit that acts as an image reconstruction model, and that 3D unit is learning structures in the bright field that are not perceptible to the human eye, but information-wise are still present in the bright field image, and it's able to predict the fluorescence target in the cell with relatively high accuracy. So I guess what we have achieved here is, without having to shine laser light on these cells, through just bright field imaging, we are able to visualize what some of the internal structures are going to look like. Again, this is not going to be possible for every internal structure. Maybe the mitochondria will do very well, maybe the nucleus won't, but at least if you're able to take off like 50% of the internal structures and just predict them using the information available in bright light, you have reduced the photo damage to the cells by 50%, and you're studying a lot more sort of healthy or rather unchanged morphology, if you will, right? So that's again computer vision model sort of playing a key role in reducing, automating the experiments. It reduces time, number one. It also reduces photo damage, and so you can essentially sort of construct just the ideal pipeline would be just you have this bright field stack of images, and you are literally able to predict using unit or whatever model you pick all of these different stained channels, and then you can sort of false color them and merge them together, so you can sort of see all of them together in one image, all coming from a vision model. So I think that sort of brings me to the end of my, sorry, there's one last plug for what Calico does. So here again, this is what we call a lifespan machine, a yeast lifespan machine. These little structures here are traps. So these are different wells in an assay. So these are traps, and here in the middle you see a cell. So that's a yeast cell. And what we care about, this is yeast cell, and this is called a budding yeast cell. The budding yeast cell, like it keeps budding daughters, and the life of a budding yeast cell is not measured in chronological time. It's measured in the number of buds it produces. So the cell typically produces like 20 buds and dies, or something like that. So this machine is an automated way of, I'm not showing an animated here, but essentially you can actually do a time-lapse video of this where the cells are actually budding in real time, and you can literally count using like a Mascar CNN or some other machine vision model how many times the cell is budding. And this is what is called a survival curve. So this is the replicative age, the number of times the cell buds. This is the probability that the cell is going to live. And essentially what we see here is that when you perturb the genetics and the environment, they can alter the lifespan. So the blue curve here is how a normal yeast cell would, in a population, again, I'm not talking about one cell. If you look at a population, on average, the yeast cells kind of have a survival curve that looks like the blue one. So after about like 50 times of budding, they die. but then you can imagine a sort of different media, or maybe you give them like more sugar or whatever they like, and if you can imagine that the cells are happier for longer, and you can imagine that the survival curve is sort of moved to the right. Or you can imagine a genetic perturbation where you knock out certain genes and create these mutants, and you can imagine that the cells are going to live shorter. So again, how vision comes into this whole thing is you can create an automated experiment, you can set this up, and you can have a scope just creating these time-lapse movies, and without a scientist having to look at any of these raw images, you can literally segment out every yeast cell, you can literally count how many times the cell is budding, and you can envision a scenario where these plots just come out of the experiment. So you can create a vision pipeline that does the whole thing. Yeah, I guess that brings me to the end of my talk. So I just wanted to motivate vision in both like healthcare and life sciences. Thank you.
Thanks, Jagadish. Does anyone have any questions for Jagadish?
Thank you. First of all, thank you for the fantastic session. Now, I just want to know, when you're doing this, the postdoc study, when the scientists are actually looking at the images,
yeah.
All these images are coming out from a microscope, and I gather that would be streaming data.
So these are mostly, are you talking about the last slide?
Yes.
Yes. So
I mean, the slide before the last slide, I'm sorry, I couldn't see the number. The one before this, yeah, this one.
Okay.
So when you're actually having a pipeline coming in through, are you doing all the processing on the cloud, or do you have any kind of models deployed on your optical phenotyping microscope?
So typically for the kind of experiments that we do, at least at Calico, a lot of these are not on the scale of like gigabytes or petabytes of data. So most likely the scientists are sort of creating these genetic perturbations. They want to understand what happens to like tens of thousands of cells.
Right.
And that informs them of the biology, and they can move on to the next steps.
Okay.
So typically we just deploy it either on our local cluster or on Google infrastructure, basically.
Okay, but just one more question around that. Won't the scientists be wasting a lot of time in terms of identifying the good images from the bad images before they actually do the processing on that?
So it's beyond that. So it's basically trying to segment out, like when we are imaging these guys, we are actually imaging populations. So in a particular field of view, depending on like how much sort of microscope zoom you have, you get like 100 to 1,000 cells in a particular view, right? And then you want to go and see what every cell in that field of view is doing. So essentially the statistics we are deriving are from the population. So the first step is to really go and segment out every cell. So you can use like any semantic segmentation or instant segmentation model to do that. And then once you have that, you can crop out the region of interest for each of those cells. And then what you want to measure on these channels, for example, if I want to understand what is the endoplasmic reticulum doing, it's either you can imagine an embedding space where you can just, let's say a model is trained on ImageNet, right? And then you just pipe this cell image through that, and you look at the feature vector that comes out before the last layer or whatever. So you have this embedding space representation, which is not interpretable. I don't know what the numbers mean, but I have this 1024 dimension vector, which is showing me some features of the cell image that came in. And if I am able to compare at a feature level what a healthy cell is doing versus what a sick cell is doing, and perform some sort of clustering. So that is the kind of downstream analysis that the scientists want to do at a population level.
Can I ask one more question?
The last part is extremely important. Now, when you have a large, when you're taking the image vector, is there any kind of computing that you're doing to give it a mathematical value that says that these images are good, like calculating a Shapley value?
Absolutely. So it's extremely well studied, and like traditional, before deep learning came along, basically like people were hand engineering these features. Literally they were creating features like the shape of the cell, the size of the cell, the eccentricity, the intensity, and all those kinds of things. And then there is this thing that came out called the cell profiler, which MIT created, which is like 3,000, 4,000 features, which over time they essentially collected. All features they could think of that could make sense. So obviously it is riddled with features that are just noise for the particular phenotype that you're looking at. So it's, if you can sort of take them out, good for you. But essentially you can imagine a scenario where you have this, where you're featureizing an image, either based on a standard template, or if you don't know what you're going after, you can actually create your own custom classifier and try to featureize them as well. Yeah, sure.
All right, let's thank him again once more for the talk. Jagadish, thank you. All right.